Hello students, so in this lecture we shall be talking about photoelectron spectroscopy. It is PES. Now, photoelectron spectroscopy is used to probe atomic and molecular energy levels. And what happens is that the atom or the molecule are subjected to high energy radiation. They are subjected to high energy radiation, and after that what happens, the electrons are ejected. Suppose we have the levels here, and you have atoms, molecules here. So whenever there is an incoming of an high energy radiation, H mu, the electrons are ejected. So there is always a binding energy. There is always an ionization potential. And there is always a binding energy involved. So once the kinetic energy achieved by the electrons, it overshoots its potential, an electron is ejected. And the electrons ejected, and these electrons have different velocities depending upon from which energy level they are coming. Now, what actually the photoelectron spectroscopy does, it measures the velocity distribution of the released electrons. Main role of PES is to measure the velocity distribution of the released electrons. Now, as we have discussed about ionization potential, so ionization potential, or IP, this is basically the least energy required to remove an electron. From the highest occupied energy level. binding energy, the term binding energy, which is actually obtained in photoelectron spectroscopy, this binding energy is the electron, the energy with which the electron is held with the nucleus. Electron held with nucleus. And if the photon energy, as we have seen, if this h nu, incoming energy of the incoming radiation, or the photon energy, is greater than the binding energy, so it will cause the electrons will leave the atom. Electrons will be ejected, and they carry with them the excess kinetic energy. The excess Ke. So if you write it in terms of an equation, it will be h nu is equal to binding energy plus kinetic energy, and the kinetic energy is then equal to h nu minus the binding energy. So this is the conservation of the total energy. So we can also write that the total energy is conserved. So what we actually conclude is that if we know the monochromatic exciting radiation, then we can measure the binding energy of the electrons in the atom, and under examination by observing the kinetic energy by which they leave. If the atom is a part of a molecule, and then the energy of its valence electrons and to much lesser extent its core electrons will be modified by the bonding. So energy, so when atom is in a molecule, when they are associated with bonds, they are linked to other atoms with bonds. So in that case, the energy of the valence electrons of a particular atom and also the core electrons, but to a lesser extent. They all get affected. So they get modified. So them get modified. Now let's take that we are using an helium lamp, and which has got a wavelength of 58.4 nanometers. It's in the UV range. In X-ray photoelectron spectroscopy, we are using X-rays as the high energy radiations, and we are the electron bombardment of a clean metal target, and we are producing this X-rays by electron bombardment to a metal target. which is mainly aluminum or magnesium or copper. So with that we get different radiation. For example, if it is a copper, K alpha copper, so the wavelength is 1.54 angstrom, and if it is a K alpha aluminum, so it is a 14.1486.6 electron volts. Now, if a very high intensity source is required, synchrotron radiation can be used. So if very high intensity source required, use synchrotron radiation. Now, this synchrotron radiation has the advantage that its emission frequency can be tuned over a range. So we can see that it has got a tunable emission frequency, and it can be over a range, it can be tuned, and the energy levels, as this is quite obvious, that the energy levels for different values of the principal quantum number, if it is 1, 2 and 3, the energy levels are K, L and M and so on. And if we use it, for example, there is another way of representation. That means if the term symbols are, say, 1s0, 2s, 2s0, 2p 1/2, and 3p 3/2. Then the X-ray rotation symbols are K, L1, L2 and L3. So the subscript denotes the sublevel from which the electron is ejected. So, subscript, it tells you about the sublevel from where the electron is ejected. So the binding energy of electrons in free atoms of, say, binding energy of electrons in free atoms of say hydrogen, lithium and fluorine. For hydrogen, it is the one state or the K state, and the baric energy is 13.6 electron volt. For fluorine, for lithium again, there are two states. One is from the K states, as in the case of hydrogen, and the other is from 2s state. So this is L1. So it is 58 electron volt. And this is 5.4 electron volts. For fluorine, on the other hand, we have three states. That is one state, that is the K state, 2s, that is the L1, and 2p. So 2p corresponds to two states, L2 and L3. It means that it is 2p half and 2p 3 by 2, and the corresponding band energies are 694 electron volts for this case, 37.9 electron volt, and for this case it is 17.4 electron volt. So as we have said that there are two ways by which we can generate the photoelectrons, either it is a helium lamp or a UV light. So that is called an ultraviolet photoelectron spectroscopy, and if you are using an X-ray, then it is called an X-ray photoelectron spectroscopy. Now in both XPS and UPS, the electrons that are ejected, they are measured by using a hemispherical analyzer. And the photoelectron spectrum is a plot of the number of electrons emitted against the kinetic energy. For example, if we take argon in the gaseous state, and here an electron is ejected from the 2p orbital. So the configuration of the argon is, you know, is 1s2, 2s2, 2b5, 3s2, 3b6. So here this is from where the electron has been ejected. Now, because the possible combination of L and S that is the LS coupling, they result in two slightly different energy states. That means it's 2p 3 by 2 and 2p 1 by 2 due to the LS coupling. So we get two different peaks. That means we get a peak like this when we plot with the binding energy. So this, the first peak corresponds to 2p1 by 2, and the second one is for 2p 3 by 2. So it is assumed that when the 2p 3 by 2 state is formed, so since this 2p 3 by 2 has got more binding energy, so if we go by the equation that we derived, the kinetic energy is equal to h nu minus p. So that is why for the 2p 3 by 2 state, the electrons will have slightly less kinetic energy. Now, the probability of ejecting an electron from a particular energy level will obviously depend on the number of electrons in that level and originally present. So, probability of ejection it will depend on the number of electrons in a level. And it is actually the degeneracy, you can also call it the degeneracy. And this degeneracy can be obtained if we measure the area under the PES peak. So its measurement will be the area under the PES peak. So this area will give you the degeneracy. Also we can say that since this is having a more magnetic energy, so we can say that the chance of forming an ion in the 2p 3 by 2 state, so chance of forming ion into 2p 3 by 2 state is twice that of 2p1 by 2 state. This is twice of that in 2p1 by 2 state. Now, another way of representing it as we are representing the degeneracy on each level. So if we take 2 by 3 by 2 state, so it has a value. So it is actually okay. So this is actually the J value. This is actually the J value. So this 2p half and P. So these are the two G values. That means when we are considering the electron LS coupling, that means L is equal to 1, L is equal to 1 for the P state, and S is 1 by 2. So when they couple, so it becomes S plus 1, so it is 1 plus 1 by 2, so it becomes 3 by 2, or 1 minus 1 by 2, that becomes 1 by 2. So these are the J levels that we talked about. So if you consider these are the J levels, so the degeneracy is again 2J plus 1. So for the 2P 3 by 2 state, 2J plus 1 is equal to 4, and as for the 2P 1 by 2 state, the 2J plus 1 is equal to 2. So that also justifies the fact that the chance of forming an ion is twice in 2p3 by 2 states, because the degeneracy is twice compared to the 2p1 by 2 state.